In this video, I will tell you a few things about plant evolution. It's a very broad topic. I can't talk about everything here. Instead, I'll just give you a few facts and ideas. So, first, it may seem obvious, but plants have not always existed. As for all other forms of life, there was a beginning. To give you an idea on the geological timescale, Earth is about 4.5 billion years old. And life itself dates back to about 3.5 billion years. On the other hand, land plants are much more recent, since their last common ancestor has been estimated to roughly 470 million years. So just to be clear, all of the dates given here are approximate. Some are still being debated. We provide them here only to give you a general idea of the timescale. If we zoom on the last 500 million years, we think that seed plants, the large group that includes flowering plants and conifers, dates back to about 320 million years. To give some context, back then there were no mammals or birds yet, but terrestrial and aquatic animals were already quite diverse. On this timescale, flowering plants are remarkably young. Indeed, the oldest known fossils of flowering plants are about 140 million years old. This is still quite old if we remember that dinosaurs became extinct only 66 million years ago, with the exception, of course, of birds, which are little dinosaurs with wings. So the extraordinary diversity of flowering plants is the result of only 140 million years of evolution. During this time period, flowering plants became progressively dominant in most ecosystems. Today, it is by far the most diversified group of land plants. About 9 in 10 plants are flowering plants. As you might know, we have been thinking of evolution for only about 250 years. More precisely since 1859, which is when Charles Darwin published the first version of The Origin of Species. Already back then, at the same time when he proposed his theory of variation and natural selection, Darwin imagined that it would be possible one day to reconstruct the genealogical tree of all living species to represent their evolutionary history. Today, this representation, called phylogeny or phylogenetic trees, has become a universal tool to understand the evolution of all groups of living organisms: plants, animals, fungi, bacteria. The tips of the tree represent living species, those present at time zero, in other words, right now, as all plants, ourselves, squirrels, ants, all living organisms. The nodes of this tree, if we go down this figure, represent the ancestors of these species, those that lived in the past. So the way to read this tree is from top to bottom if we want to go back in time. In addition, this tree has now become the basis for the classification of all flowering plants. This is the APG system. However, phylogenetic trees are not only useful for classification, they are also primarily useful to understand the evolution of all forms of life. So now I'm going to give you an example. This is a simplified phylogeny of all land plants. These include mosses, lycopods, horsetails, ferns, conifers, and flowering plants. Just to be clear, here I am really simplifying the story. This is only to give you an idea of what this tree looks like. So this tree allows us to trace back some important events in the history of land plants. First of all, the emergence out of water, which characterizes all of land plants. Then, the origin of vessels, which characterize all the so-called vascular plants. This tree also allows us to show the origin of seeds, which characterize all the so-called seed plants. In other words, the group that includes conifers, a number of other small plant groups in flowering plants. Last, this tree allows us to note the emergence of flowers, which characterize all flowering plants. To clarify, this tree certainly doesn't mean that flowering plants are more evolved than other plants. It all depends on the context. So how can we go back in time to reconstruct plant evolution? All that we can see today is the result of evolution. We only see living organisms in all their diversity of shapes and forms. With this diversity of living plants, it is far from obvious to reconstruct the past from only the present. And yet, this is what we do. How does it work? Let's imagine flowers with 3 petals and other flowers with 5 petals. In this situation here, it is quite easy to imagine, with this phylogeny, that these 4 species with 5 petals share a common ancestor, which also had flowers with 5 petals. On the other hand, the common ancestor of all these plants probably had an ancestor of 3 petals. Indeed, the simplest scenario is the one involving a single transition from 3 to 5 petals on this branch. But if one of these species instead had 3 petals, then things become more complicated. There are 2 possibilities. Either we keep the same scenario, but with a transition back to 3 petals in the species. This is what we call a reversal. Or the 5 petals evolve twice independently in this group. This is what we call convergence. These 2 processes, reversal and convergence, are very interesting from an evolutionary point of view. For instance, the loss of limbs or legs in snakes is a reversal compared to their tetrapod ancestors, which themselves, as you and I, are derived from ancestors that originally lacked limbs and look more like what we would call fish. So how do we reconstruct phylogenetic trees? The easiest solution would be to use direct traces from the past, in other words, fossils, in order to reconstruct phylogenetic history. Unfortunately, this is impossible for most living groups. With just a few exceptions, for most groups, especially plants, we know some fossils, but there are not enough fossils to reconstruct phylogenetic trees with precision. So initially, biologists started to use the morphology of living plants to trace back their phylogeny. Today, we rather tend to use DNA for this purpose, roughly since the 1990s. So it is thanks to DNA and to more and more powerful computers that it is possible now to evaluate among the thousands or billions of possible phylogenetic trees, which ones best explain the data we observe now. So to summarize what I have told you here, all living forms are the product of evolution. These may reflect adaptations to particular environments, recipes that allow plants to survive and reproduce faster and better. But to be clear, not everything can be explained. Chance probably also played an important role in evolution. Things that we see today are simply things that survive to this day. So no species are more evolved than others. It all depends on the context. So for instance, this plant here and me, we both share a common ancestor that lived about 1 to 2 billion years ago. It is neither up to me or this plant to say which is more evolved. It all depends on the context. To finish, it's important to understand that we don't know everything yet. There remain many enigmas in evolution. And one particular enigma in plant evolution is the exact age of flowering plants. There's a lot of research at the moment, and we still don't know how old exactly flowering plants are. So just to finish, I'd like to present you 2 important people. Come in here. So this is Daniel Mathieu, who played a key role in creating the MOOC for which this video was originally made. So Daniel is the founder and president of the association Tela Botanica. And come on here. And this is Julia Barbelan, who was the cinematographer for this particular video and the entire MOOC Botanic that we created together.